How is everyone today?
Good. Pretty good.
Cool. I'm going to be sending out a short survey later on today probably. It will show up as an ungraded Canvas quiz, but I'm going to send an announcement and ask everybody to take this quiz for me. Regarding your plans and intentions for CSE222 and possibly CSE215 in winter, we're trying to figure out a classroom that will accommodate all the students who want to take the class in person, and it would help to have a pretty accurate count of how many people are needing to take it in person. So I'm going to send out a note and I'll post an announcement, but if you can look for that and try to get it back to me sometime today, that would be great. And it's going to be like, 4 questions or something, or 2 questions. But I'll put all that in an announcement. Alright, let's do an attendance note so I know who's here. And let's begin with questions, whatever questions you might still have on PA2 or other things. Well, hopefully that means PA2 is good. I mean PA3. Again, my suggestion is if you're not completely done with the assignment, and maybe you've got everything working except the prediction function for predicting how many guesses, and maybe every time you call that function it seg faults, right? My suggestion would be, comment out that call. Turn in something that will compile and that will run and that will do as much of the gameplay as you have working. And then you can make a submission comment or a readme or something that says, hey, this all works except for the predict, which was throwing a seg fault. The code is in there, but I commented out the call so that the program would run, right? But then, you can get graded on most of the assignment because you have most of it working. As opposed to, I'm 99% of the way done, but, when you try to compile the code, it gives you an error and it doesn't make an executable. And then, other than looking at your source code, I've got nothing I can grade. So think a little bit about, in terms of getting a grade for this, what's the best strategy at this point of the game, and hopefully you're submitting along the way, so that whatever you have at each point is already in GitLab. But then you can keep working on it if you have time and inclination, and try to get those last details worked out. And if you don't, then I can still grade what you do have turned in and what is working. So it's generally worth spending some time doing a little bit of strategizing on getting points. You don't want to make that the whole focus, because then you can kind of miss the bigger lessons. But it's totally legit to take that into consideration if you're not completely done. Alright, so no questions on PA3 or anything else? So let's talk more about GDB. And I posted on Canvas yesterday this sort of like half-page, just a list of the commands that we've used or that we're going to use. And this is just kind of like, tip of the iceberg, right? This is how you compile with a G switch to include debugging. This is the GDB command itself. Start begins the program so that we can do debugging. List shows you your source code. Print will let you examine the values of variables. Step and next, we'll do a step into or a step over to go from one line to another. Break will let you set up a breakpoint, which says when you get to this line of code, stop, right? And come back and ask me for instructions. And if we've hit a breakpoint and we want to continue running until we hit another breakpoint, we can say continue. And then P lets us print the value of a variable, or print, right? So you can abbreviate these things. And that's probably, 95% of what you're going to use in GDB at this point. And we can also set breakpoints for when a variable changes. That's what a watch point is. So we can say, watch count, and anytime the count changes, we'll get a message saying, count has changed, the old value is this, the new value is that. And our debugger will sit there and wait for instructions from us. And that's really useful when you have a flag, for example, that's getting set, and you don't know where it's getting set. And according to your code, it should not be getting set, but it is. So you can put a watch point on it. And as soon as that flag changes value, you'll come back and you'll see exactly where you are in the program. And so that's a useful one. So we had played around with an initial program, a counting the number of e's function, count e, and the problem here was that our counter was not initialized. So when we said gcc-g main1.c, and we say start, then we say step into the count e function, and we print the value of c inside our loop, it's already got some bizarre value because it hasn't been initialized. And so, when we find the letter E, it will increment this from big number 89 to big number 90, right? But it didn't start at 0, so it's not telling us what we want. So we should have just, initialized C, perhaps in the declaration. So when we said integer C, we could have said integer C equals 0. All right, so I have some other versions of this, and each of these versions has some issues, and so I'll show you the source code briefly. I'll show you what the program does, and then I want to use GDB to sort of narrow down where the problem is. And again, you might be able to look at the code and just see what the problem is, but we want to figure out how we could do that sort of systematically using the debugger. So let's take a look at main2. And so, same thing, let's call count e with hello by, let's count the number of e's. Here's our count function. And I'll compile that and I'll run it, and hello by has 2 e's, so this should give me a 2, but it gives me a 0. So let's compile it. We'll put the -g switch in, and then to run it we'll say gdb main2, and I'll say start, and I want to go inside my count e function, so I'll say step. I'm initializing C to 0. So before I make this statement, right, C has some weird value, but once I initialize C to 0, it's 0. So that's well behaved. And now I'm going to go through my loop. So my argument is hello by. So this should go from 0 to 1 less than the string length. The string length should be 9, so it should go for I from 0 to 8. And I'm going to say if arg bracket I is equal to E. Well, there's the value of I. Here's the value of arg bracket I. That's an H. Alright, so it's not going to execute this if statement. So I'll say next. And all of a sudden it's going to return my value of C, which is 0. So I never looked at the other characters in my string. I looked at character 0, which was an H, It's not equal to an E, so I didn't increment my count, but now I'm returning. Why didn't I do the rest of my loop? Why didn't I look at my other characters? So I can say, let's list count E. And there's what my function looks like. So what's going on here? And let me run this again. Say again?
Could it possibly be like the for loop area where I is less than the string?
So my argument is nice and long, and I is still 0. So I should be in this for loop still. So let me run this from the start again, and let me do this without any interruption. Right? So there's a cleaner picture of this without, printing variables in between and sort of interrupting that visual flow. We got into our function, we set C to 0, we said for I equals 0 all this, if the argument is equal to E, which it's not, and then it does a return. So clearly it's returning too soon. Right? In particular, it's returning while I is still equal to 0. So can we see something in here?
Are you missing a semicolon after the I plus plus? You're not supposed to have a semicolon?
I could put a semicolon, it wouldn't hurt, but that's not causing problems here either. But that's a good thought.
Oh, you're using 2 equal sign for...
That's good, that's a comparison. So I'm trying to see if our guy is equal to the letter E. Ah, so someone spotted it in chat. And yes, you are correct. Anybody else?
Oh, you have the return inside the for loop.
There we go. Excellent. All right, yay, good catch. Yeah, so my return is actually inside this for loop. Now it's indented over here, so visually it kind of looks like it's outside. But if I actually go into the editor and I match my brackets, I'll see that this is actually going to happen after the if statement right here. And so the first time through the loop, it just immediately returns.
Yeah, that closing bracket for the if statement kind of looks like you closed out the for loop, but obviously you didn't.
Right. So my for loop ends here, and so that's inside. And if I had indented it like that, then it's pretty clear. And if I got rid of this bogus space up here, now it's pretty clear, I'm returning inside the loop. Alright, cool. So that's a really hard one to see. But, with the debugger, it at least kind of forces our attention pretty close to where the problem is. And we still might not see it, but, if we had 1,000 lines of code, it's nice to know there's something going wrong right inside here. And then we have a better chance of figuring that out. Alright, so here's main 3. And I'll compile that. That compiles fine. I'll run it. It tells me result is 0. So let's add debugging symbols. Let's GDB it. Let's start. Let's step inside our county function. So C is equal to 0. For I equals 0, less than string length arg, I plus plus. if arg bracket I is equal to E. So I'll print the value of I is 0. I'll print arg bracket I, that's an H, arg bracket I. What am I doing here? So what's going on here? You want to see it again? So we're inside the count E function. C is equal to 0. We'll say for I equals 0, I less than string length arg I plus plus. We'll check arg bracket I, and then we're doing a return. And if I look at the value of I, it's equal to 9, even though I initialize it to 0 in my for loop. Why is it 9? This one is super, super sneaky.
And that's with only one step through the loop, right? It hasn't been incrementing it the whole time.
Yes, why? That's the behavior we're seeing, right? We got down here, we're ready to execute the for loop. We did the if statement, and then we did the return.
Is that semicolon at the end? That's just using it as one line, right? Just incrementing everything.
Yep,
That's just a one-line for loop.
that's the culprit right there. So the semicolon, since we don't have curly brackets after this, the semicolon says, hey, everything between that closing parentheses and the semicolon, that's the body of the for loop. That's the stuff you want to do each time you iterate. And there's nothing in there, so it's an empty for loop. So all it does is set I equal to 0, keep incrementing it until it's equal to the string length of arg, and that's the end of the for loop. It's done. Now it comes down here, it does our if statement. The if statement doesn't fire, and then it comes down here and it does the return.
I forgot that C won't complain about that, yeah.
Yep. Yeah. So C is really kind of like, buyer beware. You tell it to do something, it will try really hard to comply with that. Even if it's something that, a more modern compiler would say, hey, wait a minute, there's nothing in the body there. So yeah, that semicolon
yes,
is
that's why
causing.
those licenses say no warranty involved.
Yes. All right, good. So that's main 3. Let's look at main 4. So no semicolon after the for loop. That's good. And if I run this, it tells me my result is 10, even though I'm calling it with hello bye, which only has 2 letter E's in it. So let's see why our count is getting up to 10 instead of just 2. So let's start, and let's step, and initialize I to 0, go into our for loop if arg bracket I is equal to E. Okay, what's I? It's 0. What's arg bracket I? That's H. Our if statement should not fire. And then we go back to the top of our for loop, and so now I is equal to 1. Arg bracket I is equal to E, so this if statement should fire, and it says increment I. But if I look at I, now I is equal to 2. And why is it 2 when I've only seen 1 E so far? And I'll come down here if our guy is equal to E. It's not. But I is equal to 3 now. So somebody got it in chat. What's the issue here? Two people got it in chat. This is a real obvious one once you see it. Like so many bugs. But until you see it, it's not obvious. Right? We're using the same variable I for counting the number of E's as we're using for our for loop. We're mixing our variables together. And really all we needed to do was, have a different variable, like count, for example, to represent the number of E's we've seen. And then here we would say increment count, and here we would say return count. And I would just be used for our loop variable in our index. So that's just a late night, kind of typo thing, where we just kind of went overboard with the variable I and used it for two different things. And, staring at this will not, reveal that to you usually. Maybe if you take a nap and come back, but this looks perfectly fine, this looks perfectly fine. You got to kind of think about those together. And if you can't do that, but you can run this in the debugger, right? You can watch how this count changes and see that it's changing each time you go through your loop, and that may help you to see what's going on, right? Why does I keep incrementing when I didn't execute the statement? And you might suddenly see, oh, I've got an increment there. That's a great Einstein quote. I don't know exactly why I is used as an index variable, other than, index starts with that. But in Fortran, at least in Fortran 4, you didn't declare types of variables. Variable type was based on its name. And I through, I think, N maybe, were integers, and things before and after that were reals. And so the first integer variable that you had available by default was I, and that's what we used for loops and stuff. But there's probably an older legacy before that, and I don't know why the writers of Fortran decided to make I the first integer. Except that Fortran was, it stands for formula translation, I believe, and it was a way to take scientific formulas and compute their values using a computer. And I is just a very popular variable when you write things like summation symbols. If you want to express how to multiply two matrices, you do a sum from I equals 1 to this, sum from j equals 1 to this. And I don't know what the origin of that is, but that would be cool to dig up. And enjoy your I's, because like I say, I know some other teachers who will forbid you from using I for a variable name in your code, and you'll actually lose points if you have any variables.
Just a regular variable, or like indexing?
Say again?
Like for any, like if you were just trying to put like a value to I rather than indexing, is that what you mean? Or like using I at all in your code to get you lost points?
Oh, yeah, I know some teachers who will say you cannot have any variables that are only one character long. So you can't have an I or a J or an X.
Really? Even like a function?
Yeah, well, so there's all kinds of dogma out there. A lot of it for good reason.
Yeah.
I've had students come back to me and tell me they lost, points because they did for j equals 0, j less than this, j plus plus, and the teacher took off points because they wanted them to use I instead of j. So there's all kinds of things like that. I try not to be too dogmatic here, so this is like playtime. All right,
It's an acceptable one.
J.
Yeah, because like if you're going up and down a array,
Mm-hmm.
left and right and up and down an array.
Yeah, so you can use J for an inner loop, but in this one class you could only use J inside another for loop. You couldn't use it for the outer one.
Well, usually the outer one is I, right? And the inner one is J.
That was what the comment was I is used for outer loops and J for inner.
Yeah.
So, but that's okay. When you get a job coding for other people, a lot of times all of these things are dictated to you, and including how far you have to indent your statements, where you have to put your curly brackets, what you have to name your functions, whether you use camel case or snake case, and so on and so forth. A lot of that stuff is dictated because you're writing code with a bunch of other people, and they want a uniform appearance and structure to these different pieces of code so that it goes together more easily. And that's okay. If someone's giving you money to write code, you can write the code the way they want, sure. But it's one good reason why it's nice to be able to sort of switch around. On the other hand, when you're in that kind of situation, you're probably writing code in something other than VI. You're probably using some sort of IDE that's doing the formatting for you. And you might indent 4 spaces, but as soon as you hit the enter key, it changes to 2 tabs, So, but then you can always go home and turn off the lights and close the windows and write code the way you want. So that's always good. All right, let's take a look at main 5. So same thing. I've got different variables. I'm back to using count for my counter and I for my index. And let's try this. And I'm counting e's in the string hello bye. And I've got a print statement telling me each time I find an e to help me debug. And it printed out, exactly twice. It found an e 2 different spots. But my result when I came back from the function call was 9 instead of 2. And I return count, yeah, which should be the number of e's. So let's debug this. So I'm inside my count e function. Count is initialized to 0. I is going to go from 0 to string length I. So I'll start off with I is 0. Arg bracket I is h. That's all good. And for some reason, it's setting count equal to count plus 1. And that's weird. So let's continue. So I is equal to 1 in this case, and arg bracket 1 should be the letter E. So it prints out, hey, I found an E. There's our print statement, and it increments count, so that's fine. And then if it's equal to E, well, it's not, but it still increments count. So somebody spotted this already, which is great. So what's the problem? Why is the count always incrementing? There we go. All right, people see it, right? So using the debugger, we're forced to the realization, hey, my count is always incrementing, even if this if statement is not true. And so we know there's some problem right here, and yeah, people are finding it. So we need a curly bracket after the if statement because we have two things that we want to have in the body of the if. And without the curly bracket, this is my whole if-then statement. If arg I is equal to E, print this out. And then the count equals count plus 1 is outside that if. It's always going to happen. So the indenting is working against us, right? If I had indented this properly, the count equals count plus 1 would start over here, and I'd see immediately, oh, that's an unconditional statement. And this can happen, for example, what might happen is, you know, we had something like this, and maybe we had some other bug. Maybe we weren't initializing count, or we were doing something else, right? And we were trying to debug this, and so we said, well, let's put in a print statement, right? So I type a print statement right there to see when we satisfy this condition, and I've just introduced a new bug, right? By doing that, I moved this count statement to be outside the loop. Now, if instead we stuck to the habit of always putting if statements bodies inside curly brackets, right? Then if I wanted to add that extra statement, right, my if statement still works. Both of these things are now inside the body. But the danger is sometimes we're writing in a hurry, and so we don't bother putting in the curly brackets, we just do this. Well, this will work great as long as we remember that if we want to add another thing to the body of the if, we need to put those curly brackets in. And if you forget that, then, you know, you silently create a new bug while trying to fix an old bug. So that's a pretty subtle one too. Alright, and then everybody's favorite bug. So here's main 6. I got rid of my print statement. I'm initializing count. I don't have a semicolon here. I've got, you know, curly brackets around the if and so on. Let's run this. And so this one I had it enter a string and then count the number of E's in that. So I'll just say hello test. And it tells me it found 11 E's. So let me run this. Let me say start. I'll do the print statement, and I'll do the fgets, and I'll say hello bye. And now I'm going to go into my count E function. Okay, I'm in count E. My argument is hello bye. That's good. My count is initialized to 0. That's good. I'm going to go through my for loop. My I is equal to 0. My first element of my string is H. I'm incrementing count. Yeah, you're fast. Excellent. Somebody sees it already. So I'm incrementing count, right? Even though this first element is not equal to an E, it's equal to an H. So we'll go through this again. I is equal to a 1. If I print arg bracket 1, that is an E, so that should increment my count. That's fine. I'll go through it again. I is equal to 2. Print arg bracket I. That's an L. That should not increment my count, but it does. And you know, we already checked arg bracket I and it was not equal to E. But wait a minute. Arg bracket I apparently is equal to E. Even though I is equal to 2. What is arg? It's elo by. So I think most people are starting to see this now. Alright, so what's the problem here, right? Single equal sign, right? Hardest bug to find. This is doing an assignment, right? It's setting element I of this array equal to the letter E. And then an if statement will look at the value of this, which is the letter E, the ASCII code for E, which is non-zero, so this condition is considered to be true, and it executes what's in the body of the statement, which is count equals count plus 1. So as I'm running, this will change the value of my array, and then decide it's, you know, equal to E, and go ahead and count it. And so when I'm done, I just get back, you know, the length of my entire string. And it's actually changing my argument. So yeah, equal is assigned, double double equal is equals. And if I hadn't done that fgets in the beginning, if I just used my usual test case where I called count E with this hardwired string, and I have this bug in here, I actually get a seg fault. And you know, if you get a seg fault from your program, it just says segmentation fault and you're done. But if we run this in GDB, and we say, you know, just continue, just keep running, when it gets the seg fault, it tells us exactly what's going on. We're at line 18 of main7.c. Here's the statement that was being executed, and it caused a segmentation fault. And so in this case, that brings us down to an exact line of code where we can see something funny is going on. We're not comparing to the letter E, we're setting equal to the letter E. And the reason this is seg faulting is because when you hardwire a string like this, it's loaded into an area of memory that's read-only, specifically to avoid situations like this where you mistakenly try to modify the contents of this string. So hello bye is stored at this location in memory, and we can't modify that location. If we try to write something into that location, the memory management system says segmentation fault. So then we would go back, we change it to a double equal sign, we'd try it again, and it would work. So that's main 8. And if we run main 8, it tells us, hey, the result is 2. That's good. So that's just an idea of you know, some of the more subtle issues that can come up, and how using a debugger can kind of help to bring your focus closer, at least, to where the actual issue might be. And you still need to know, you know, what you're trying to do, and you need to know what you expect your variables to be equal to, what you expect the program flow to be like. But then the debugger is kind of, you know, the outside entity that's showing you what's actually happening. What are the variables equals to? What are the steps that are executed? What's the order of operation? And when you can find a disconnect between that and what you thought was going to happen, that's your access to the bug. And really, with all of this, you know, we've used start, print, step, next, and occasionally break and continue, and that's kind of it. And for the stuff we're doing in this course, that's probably all we need to know as far as GDB. But we can do other things. So for example, I could say, let's watch the value of count. And anytime the count changes, I want to know that this has happened. So I'm just going to say continue, and it's going to tell me, hey, count was equal to this weird value, now it's equal to 0. And I'm about to execute this statement. Well, this was the statement that just executed. That was where I initialized count. So I can say continue, and now it's telling me, hey, count was equal to 0, now it's equal to 1. And I'm at the top of my loop. So I can print the value of I is equal to 1. I can look at arg bracket I, that's equal to E. That's why my count changed value. And if I say continue, it'll tell me, hey, value just changed from 1 to 2. I was equal to 8. And if I look at arg bracket 8, that's the end of my by. Let's see. Question: are there any operating systems that don't throw seg faults for these memory access errors? Are seg fault exceptions something I can take for granted, or do I need to be careful unlike an embedded system? Yeah, exactly. So a lot of systems will set up memory in such a way that, you know, if there's something that it expects to be only read, it will make that memory read only. If there's something that it does not expect your program to access, it will make that, you know, no access, no read, no write. And that can save us from ourselves in a lot of cases. But that's a function of the memory management subsystem mainly, which is, you know, a large physical component, and it's also integrated with the operating system. And so there's a lot of overhead involved in that. Now, if you go to something like an Arduino processor, a little, you know, credit card sized, you know, $2 or $3 CPU, there's no such thing as seg faults per se. You can more or less access any area of memory because there's no protected addresses as far as I remember. And so if you do something like, you know, go out of bounds of an array or something, you're just kind of gonna, whatever happens, right? And you can't really bank on a seg fault popping up to alert you to that. On the other hand, on a larger system, you know, like a x86 or a Raspberry Pi or something, even if you're in assembly language, if you try to access a location that's not available, you will get some kind of exception usually. And so some of that is managed at the hardware level. Sometimes you can compile your code and say, hey, I want to know if I go outside of my array bounds, and you can sort of put these guards on the ends of your array to cause an error to pop up. But you know, it depends on your environment. Yeah, and as someone just pointed out inside in chat, if you know how the memory is laid out on a system and you're very crafty, you can, for example, write things into an array in such a way that as you go out of bounds of the array, you can modify other variables inside a program. And if there's a variable which says, you know, do you have root access, and that variable is a 0 by default, you might be able to, you know, type something into an array that will overflow the bounds of it in such a way that it will write on that location in memory where that flag is stored, and you can change it from a 0 to a 1 and say, oh yeah, I've got root access. And there's you know, a lot of exploits that have been done using buffer overruns. This is why we don't use the gets function, because gets is a really easy way to do buffer overruns. And we try not to do anything that, you know, potentially allows somebody to go outside the bounds of an array. So when you use fgets, if I say, you know, fgets 120, I'm saying don't store more than 120 characters in this array. And as long as my array actually has 120 characters or more reserved, I won't overflow the buffer. But if there's other ways, like, you know, scanf or scanf, for example, will let you overflow, and so on. So yeah, those are a good source of potential exploits. All right, another command. We don't really need this a lot for this class, except maybe if we start digging into argc, argv later on. But another command is x, and x is used to examine memory. So p lets you print the value of a variable, but x lets you specify a memory location and see what's stored in that location. So for example, if I say examine this location, I see 6C, 6C, 6548. That's an hex, right? Well, these are the ASCII codes of these characters, HELL. 48 is an H, 65 is an E, and 6C is an L and an L. And if I examine the next locations, there's the ASCII code for an O. 20 is a space, 62 is a B, 79 is a Y, 65 is an E, and 00 is a null terminator. And so I could go back here and I could say examine as a character, and there's our HELLO space BYE. There's a null terminator. And if I look at the next locations, I see RESULT equals %D\n. That's where the compiler linker decided to store that string that I was going to use in my printf statement. So X is useful for really just kind of like looking at memory itself. And you know, if you try to look at a location you don't have access to, it'll say you can't access that location. Let's see, does this mean access permissions are why Windows drivers are awful? Like they run at kernel level, and since they don't have that failsafe segfault at that deep level, they can write over anything. Well, that's kind of true of, to some degree, of all system code, right? Anytime you have privileged code running, it's operating under a different set of permissions, and there may be memory that's accessible, you know, from one privilege level but not from another. And it depends on the operating system. Like VMS had, I think, 16 different privilege levels. Windows, I think, has 4. Unix, I want to say, has 2, but that doesn't sound right. But that's a function of the operating system. And there's always some areas that you're going to segfault, right? So generally, nobody can access location 0. But one difference is if I'm running privileged code and I try to access location 0, I may create what's called a panic or something equivalent to that, depending on the operating system. I'll tell you a funny anecdote of that sometime from my own past. But yeah, I don't think that's just a Windows thing. But hopefully, you know, Windows drivers or operating system drivers aren't causing seg faults, right? Because usually a seg fault is something wrong in the code, and we like to believe at least that, you know, device drivers and things like that are going to be pretty solid. Last thing I'll mention on here for GDB, just this layout command. This can be fun to play with. Layout ASM. This will give us an assembly language view of our memory, and if we say step I, which means step a single instruction, we can execute while looking at our assembly language code one instruction at a time. And for example here, this is a call quad word instruction, so I'm about to call this address. Well, this is the address where this function called string length is stored in memory. And if I do one more step I, I'm inside my string length function. So if you pulled down the source code for string length .c and looked at it and compiled it, you would get something like this, right? And this is going to jump to RIP. No, but it's going to jump somewhere else, right? But this is the entry code for string length. This is the entry code for printf. And when you get down to this level, if you're stepping through system code, a lot of times it's going to blow up. And give you some kinds of messages, but you know, I'm in __ string length _ AVX2, which is, you know, some piece of string length, and these are looking fairly system level callish. But this can be fun to just kind of mess around with, and you can print the values of your registers. So I can look at this ECX register and see that it's equal to a 4. And this is one way to learn assembly language, right? This is x86 assembler. If I did this on a PIC processor, I'd be seeing PIC code. If I do it on a Raspberry Pi, I'd be seeing ARM code. But that can be fun to mess with if you want to dig into the assembly language. All right, so we are out of time. Keep rocking on PA3. Make sure you turn in what you have by the deadline. If not, well before. And tomorrow I'm going to talk more about Linux in general. We'll go back and look at some more Linux commands, and then next week we'll move into string processing. Please send me an attendance note on the way out, and have a great afternoon, and I will see you tomorrow.
Bye.
All right, bye.